Welcome everyone to the Groundwater Remediation Case Study, Modeling an LNAPL Release webinar. Hi, my name is Drew and I'm the Surfer and Voxler Product Manager here at Golden Software, where I've also been working as the training coordinator for the past year and a half. I'm here today to detail a groundwater remediation case study where I'm going to discuss modeling an LNAPL release using Surfer and Voxler. I would also like to introduce you to Steve Boynton, who is the owner and operator of Subsurface Environmental Solutions, LLC, who is the lead remediation specialist on the project that we're going to be discussing today. So Steve, I'm going to unmute you so you can briefly tell us a little bit about yourself and Subsurface Environmental Solutions.
Great, so, thank you, Drew. Thank you, Drew. Welcome everybody. I'm going to spend just a few minutes introducing my company, introducing the site, talking a little bit about LNAPL behavior, and then I'll turn it back over to Drew and he will talk about creating the model using Surfer and Voxler. So a little bit about myself. I'm a sole proprietor operating out of Andover, Massachusetts. My company is called Subsurface Environmental Solutions, LLC. Most of my work is done as a Massachusetts licensed site professional, which is a environmental licensing program we have here in my state, but I work all over the country as well. My background is civil engineering and geotechnical engineering specifically. Founded Subsurface Environmental Solutions in 2006 and have been operating as a sole proprietor since then. Most of my business focus, probably 80 or 90%, is LNAPL sites, primarily assessment, management, and remediation. I've worked for multiple governmental clients, Corps of Engineers, Air National Guard, Air Force, as well as many private companies doing assessments of sites such as fuel oil terminals and oil refineries, as well as chemical manufacturing plants. Want to go to the next slide, Drew? Thank you. So again, my focus as Subsurface Environmental Solutions is primarily LNAPL sites, which is the focus of this discussion today. My areas of expertise zero in on in situ calculations of in situ total and recoverable LNAPL mass, which is what the focus of this talk was. I also do LNAPL mobility assessments, have begun doing lots of LNAPL transmissivity testing, and I specialized as well in 3D data visualization using Surfer, Voxler, TurboCAD, and a program that we're going to introduce today called PDF 3D. The imagery around the edge of this slide, down the right side and on the bottom, are all images that I've created using either Surfer or Voxler. So if we can go to the next slide. So the focus of today's talk, or an overview of today's talk, first we're going to talk a little bit about what LNAPL is. I see that there's a lot of consultants on the call, and most of you probably know what it is, but perhaps there's some that aren't as familiar, so we'll talk a little bit about LNAPL itself. We're going to talk about the actual site that we're working on today, description of the site, how the release occurred, what the subsurface conditions are, etc. And then I'll be turning the talk back over to Drew, and he will talk about creating the model using Surfer and Voxler. So let's talk a little bit about what LNAPL actually is. So LNAPL, for those of you that don't know, stands for light non-aqueous phase liquid. So that's LNAPL is an acronym for that. LNAPL, as most of you know, is we're usually talking about gasoline, diesel, fuel oils, jet fuels, etc., or crude oils in the case of refineries, for example. So LNAPL, generally we're talking about fluids that have very low solubility in water. While they can contaminate groundwater, they will not readily dissolve in water. And the densities of most LNAPLs fall into the range of about 0.8 to 1.0. So a real brief discussion of how LNAPL behaves. This is a site that I worked on in my home state of Massachusetts. In this case, this was a number 6 oil site, and 6 oil is a residual fuel that's left after refining out the lighter components of crude oil. Generally, it is heated up in order for it to flow through piping into plant boilers, for example. At this case, about in the middle of this image, you'll see a boring B604, and that boring was right near an underground tank that held small quantities of 6 oil that were heated up prior to distribution to a manufacturing plant. On the left side of this image is an old bridge, which was made of granite block with masonry between the block joints. And a few things about the LNAPL. So we don't see underneath boring 604, we see some clean space from the ground surface down for a few feet, and that's where the tank itself was located. We frequently find leaks occurring below the frost line, which in the Massachusetts area is usually around 4 feet. So from that depth down, you'll see some residual contamination, and it is above the water table. There are 2 water tables shown in this image. One is blue and one is red. Those are the historically known high and low at this particular site. So just below the just below the tank, oil above the water table, or 6 oil above the water table, would have flown directly vertically downward under gravitational forces. When it approaches the capillary fringe above the water table, the NAPL can start to spread out a little bit. But a continuous release of oil, as was the case in this site, will cause oil to begin to mound above the water table. And as that mound grows, pressure will start to build up and the oil will be forced below the water table. Once the oil has moved below the water table, it will generally move in the direction of groundwater flow, which in this case was from the right to the left towards a river flowing underneath this particular bridge. And one thing that's clearly evident in this case is that most of the NAPL was flowing towards the river beneath the lowest water table, which was the red dashed line. There is some horizontal migration between the high and the low, but most of the NAPL actually has to move below the water table. I think we can go to the next slide. So let me introduce the site. The site is the former Pease Air Base in the city of Portsmouth, New Hampshire. The air base is now called it's called Portsmouth International Airport. So it is a private commercial facility now, but there is an area to the north of the facility that is still home to an Air National Guard refueling wing, the 157th Refueling Wing. The Air National Guard maintains a group of AC-135 strato tankers, which are refueling planes, and these operate out of Pease Air Base. Go to the next slide, I think. A brief history of the release. There was a sudden release to an underground fueling system that was estimated as 9,000 gallons. The fueling system includes an two above ground storage tanks. Piping out to the airfield is below ground, and the piping goes through various valve vaults, and in this case, the source area is what was called vault number 4, and the release was discovered to be due to a faulty valve seal within the concrete vault. So again, it was estimated by facility records that the release was approximately 9,000 gallons. Immediate recovery efforts were undertaken, which included excavation and recovery of NAPL by putting in a temporary recovery well. And it was estimated that 6,000 gallons of jet fuel, in this case, the fuel type is JP8 at this site. It was estimated that 6,000 gallons were recovered, leaving 3,000 in the ground. After the initial recovery attempts, the consultant for this project installed an air sparging and soil vapor extraction system in the vicinity of the fuel vault. And the image on the right of this vault is the equipment shed containing the air compressor for the air sparging system and the blower for the soil vapor extraction system. And I just ask that you memorize what's in this image, because as you'll see later, we did do solid modeling of that shed to incorporate into the Voxler model. If you want to go to the next slide, Drew. If we zero in on the air photo of the site, the red circle that just flew into the site is onto the screen. Shows you the location of the valve vault, that little square in the middle of the service road, and that's where the fuel lines came into and out of the vault. And one of the lines, two of the lines go parallel to the service road that's shown, and then one goes perpendicular out towards the plains that you can see. In this image, we see the approximate locations shown in the yellow dash lines of the underground jet fuel lines, and you can also see the remediation shed just towards the right side of the image. The subsurface conditions at this site consist primarily of sands. The site is located in a glacial outwash plain. Soils are deposited as the glacier was receding and melting away, and the melt waters would flow out, forming large outwash plains containing mostly sands, but with occasional seams of clay, as can be seen in the picture on the right. That's a 1 foot section of soil, and there's a little seam of clay in the middle. The seam of clay is down around 19 feet. The depth to groundwater at the site has been recorded over many years to be between 16 to 20 feet below the ground surface. And when this study was done, groundwater was at a near historic low during a recent drought period. The sands within this formation are highly permeable, so water tables are extremely flat across the area with very shallow gradients. Go to the next slide. So this site focuses on, or this presentation focuses partly on presentation of jet fuel contamination as indicated by the measured concentration of total petroleum hydrocarbons in soil. So this would be units of milligrams per kilogram of jet fuel. Most of the data that you're going to see was generated using a field screening tool, which uses ultraviolet fluorescence to calculate the concentration in soil samples that are prepared in the field as we extract them from the ground. For those of you that are in the industry, ultraviolet fluorescence in this setup is an ex situ technique that would be similar to the technique that's used in the in situ methodology called laser-induced fluorescence, or LIF, but this is an ex situ variant. All the samples that were tested, that were prepared in the field were tested using the two instruments shown. One was calibrated for diesel range organics, the other for gasoline range organics. And a set of confirmatory samples were sent to an analytical lab for calibration purposes. And you can go to the next slide, Drew. Thank you. So I'm going to turn the presentation over to Drew here. I do want to mention that, well, I think I'll just turn the presentation over to Drew at this point. Thanks.
Thank you very much, Steve. That was a lot of detail, and we really appreciate that. So now that we've given you some background on the site and the LNAPL itself, I'm going to go ahead and move on to discuss the project that Steve used to model the LNAPL release. Before I do so, I wanted to open it up just for a quick second to see if anybody had any or the LNAPL itself or for Steve. So I'm going to go ahead and check with my host real quick to see if there's any questions that that I need to address. Okay, she's telling me that that there's no questions now, so I'm going to go ahead and move on and get into the details of how Steve created all the specific components of the model. But before I do so, I'd like to first show everyone a complete model overview so you can see what his final model looked like inside of Voxler. So I'm going to go ahead and open up Voxler and open up the VoxB project file that Steve used himself to create the deliverables for the clients. Okay, so now you can see the model for the area that Steve created for this project. And so in this project, you should first notice a number of different surfaces. Okay, and as I rotate this around, you can see them. First, we have a ground surface, right? And you can see the shed that Steve was talking about there also. And if you can see these two surfaces here, and we've modeled both the low and the high groundwater. Okay, so you can see where the mounting and the LNAPL release is in comparison to both of these surfaces. As I zoom in just a little bit here, we also see the vault, and this was that 10 by 10 by 10 concrete vault where the LNAPL release in this project actually occurred. Okay, and then you can also see the jet fuel lines going in and out. These are the transmission lines. Okay, and if I zoom out just a little bit more, we can also see the SVE pipes or the venting pipes. And again, we also have that treatment building that Steve added to his model. If I zoom out just a little bit more and rotate around, we do see some monitoring wells that were included in the project. We also see the sparge wells that were used for the remediation efforts to clean up this LNAPL. But probably more importantly, as I zoom in here just a little bit more, I'm going to toggle these on and off, and this is the borings that include the UVF data. Okay, and so this is where the data Steve used and collected to model finally this isosurface, right? And this shows the concentration, the chemical concentration of the jet fuels in the soil. Okay, and I know that Steve looked at this ISO value, the concentration levels anywhere from 2,000, and I think this is a logarithmic value, and I can have him comment on that as well here shortly. And so this was the model that Steve used to generate the 3D PDF for the project. So now I'd like to move on to discuss how Steve created this conceptual site model using both Surfer and Voxler and piece it together for everyone. So to start off with, I'm going to go ahead and open up Surfer. And we're going to start with importing some elevation point data that was derived from a LiDAR file that was downloaded originally from the USGS's 3DEP program. So in Surfer, in this new plot window, I'm going to create a post map from this data by using the home new map post command. And in the open data dialog, I'm going to navigate to this point data, which again was extracted from the LiDAR tile from 3DEP. Go ahead and click open. And so now we can see a post map of these data points, right? Change the symbol here just a little bit so we can see that they're all points, and reduce size here, but I'm showing this to show you the mere number of points that were used to create this ground surface. So in order to create the ground surface, I need to grid the data. Okay, and so this can be easily done in Surfer. In the grids ribbon here, and click the grid data button. Again, select my data file, click open. And so now we see on screen the grid data dialog. And so I'm going to make a few changes here. I'm going to make sure that my X and Y and Z columns are set appropriately. Gridding method can be set to kriging. And I'm going to adjust the spacing just a little bit here in both of the X and Y directions. I'm going to make sure that The assign no data outside convex hull is unchecked. And our output grid file looks good. So everything looks good in our grid data dialog. I'm going to go ahead and click OK to grid the data. And it's going to take just a second, as you can see, that progress indicator right there on the screen. And we'll just give Surfer a few minutes to think here while it's gridding. All right, it looks like it's getting close. All right. Surfer tells us that we're done gridding here. I'm going to click OK. And now that Surfer's done gridding this data, I feel a good way to view the new ground surface is to create a contour map from it. So this will really allow us to get the correct bounds or extent for the site that Steve was modeling, and then also allow us to download an image using Surfer's download online maps functionality, so then we can get an image overlay. So first, let me add the contour map. All right, I'm going to add to map layer. Select my contour option. Select the grid file we just created. Now if I toggle off the post map, we can see some nice contours here created for the ground surface. And as I mentioned, we're going to download an image using Surfer's download online maps functionality. But before I can do so, I'm going to go ahead and set the coordinate system for all the layers involved here. So I'm going to go ahead and click on my map, go to the coordinate system tab, click the change button, and in this assign coordinate system dialog, I'm going to drill down here into the appropriate coordinate system. State plane, 1983, of course that's NAT 83, New Hampshire, and we're working with feet. So once I have my coordinate system selected, I'm going to go ahead and change that for the top layer. And since all of our, both of our other layers have the same coordinate system, I can use this Assign Now button, and that's going to assign the coordinate system now for the contours layer and also that post layer. So now an image can easily be downloaded into our project using the home, add to map, base from server command. Okay, and so I'm going to actually download an OpenStreetMaps layer. Okay, and so I went ahead and selected the server. And since I set my coordinate system to CRS for my map and the layers, Surfer automatically populates the lat long and does a conversion for us. It populates the lat long extents, so we know where and what tile to get from the server. We've got this at max resolution since it's just such a small site. This is about as large of an image as we can download. And I'm going to go ahead and click OK and let Surfer download the map. Okay. And click clasp yes there in that Surfer warning. And as I turn the contours off, we can see we have a good looking base overlay that we can now use for an image overlay inside of the Voxler project. But before we move on to assembling the model in Voxler, this image needs to be exported from Surfer. So in the contents window, I'm going to click off the visibility checkboxes for the axes. And make sure the contours and the post layers are also checked off, as I don't want those in the resulting export. And then I can click File Export. I'm going to choose TIFF. That'll work. I'm going to name this image overlay and go ahead and click Save to export the image. I'm going to increase my resolution or my pixel dimensions by increasing the pixels per inch value. And let's go ahead and click OK. And the image has now been exported. So now that the ground surface grid has been created and the image overlay has been downloaded and exported from Surfer, I'm going to go ahead and move over to Voxler so we can display and show everyone how to assemble the conceptual site model that Steve used for this LNAPL assessment. Okay, and here's his original model again. And I'm going to go ahead and start a new network. And so in this blank project, I'm going to first start out with importing the ground surface and then the image overlay that we just created in Surfer. Okay, so I can start out in the File menu by clicking File Import. Again, we want that ground surface that we just created. So I'm going to select that in the Import dialog and click Open. Next, we see the Lattice Import Options dialog, and it's really important to get the setting right here. I'm going to choose to import as a curvilinear lattice, and this will allow Voxler to locate the surface using the correct Z level, and so everything regarding the DXFs that we're going to import and the well data and the borehole data will all locate in the correct Z level. So I'm going to select Import as a curvilinear lattice. Click OK. And so now we see the ground surface has been added to our network manager. We can add a 3D surface to this grid real easily by right-clicking on it in the network manager and going to Graphics Output and selecting Height Field. Okay, and so here's our original or our first ground surface, and this is the start of the model. And as I indicated just a second ago, I'm going to also import this image overlay. So using the File Import command, this time I'm going to select our image overlay that we just downloaded into Surfer and click Open. And to drape or overlay this surface on the height field, I'm going to need to drag the connector from the TIFF over to the height field module, and then choose Connect Input Image Overlay from the context menu. Okay. So I rotate this down. You can see both of the surface color and the overlay color are blended together. So I'm going to account for that right now by selecting the height field. Moving down to the Property Manager, and on this Image Overlay tab, we can see that our overlay is being shown clearly. I'm going to change the fit here to Clip to Surface. And that's going to ensure that it's locating at the right XY locations. And probably more importantly, I need to change the color modulation. As you can see right now, it's set to blend, which is going to blend the surface and overlay colors together. I can also choose to use the overlay color itself. It brightens things up for us a little bit. So now you can see the ground surface for the project, and this, for all intensive purposes, is the project extent that we'll be working with. Okay. And Steve did mention this earlier in the presentation, that he did create a few pieces for this model in TurboCAD. Okay, and these were namely the vault, and that was where the LNAPL was released, and then the treatment building, where they had the pumps and the compressor for the sparging wells. So I think it's a good time in the presentation to go ahead and import these 3D DXFs that he created in TurboCAD. Okay. So easily done. Again, file import. I'm going to first go ahead and select the vault and import it. Okay. Can't see it right now, but as I rotate down, right, we can see this 10 by 10 by 10 concrete vault. Of course, this again is where the LNAPL took place, and it'd be nice if we could see this through the upper surface. So I'm going to go ahead and right-click right in the right here in the window, and from the context menu, I'm going to change the transparency type just a little bit there, and we'll add some transparency here to our height field itself. And we should be able to see this vault here coming through eventually. And then we also wanted to import the treatment building. So I'll go ahead and do so now. All right. And as I zoom in, this does look very similar to that image that Steve showed us when we were talking about the site characterization. So I'm also going to import the jet fuel transmission lines, and we saw those as the yellow dotted or dashed lines in one of the images that Steve was discussing earlier. And for these transmission lines, Steve used a unique application of the well render module directly inside of Voxler, where he used the well render to create the pipes. But to save time today, I went ahead and exported these transmission to jet fuel transmission lines from Steve's project in 3D DXF format, and I'm going to import these into the project at this time. Okay, and go ahead and just turn this height field off for a second so we can see this. And now you can see the jet fuel transmission lines. Okay, and again, Steve actually used a well render module to create these. And if I toggle back to his project, and you can see these lines right here. And let me go ahead and highlight these real quickly. So he used a well render, which is right here. And we can take a look at the data, how Steve organized the data real quickly. And so this is a real simple table of top X, Y, and Z, a little bit of azimuth, and some depth and some length. Okay, and again, this was a real unique application of using the well render to create pipes. I do have an article that I've written on our website. If you guys have interest in finding more information about how to do this, please let us know, and we could forward you a link to that article. Okay, so back to our model. It looks like it's coming together nicely. Okay, and so the next step here would be to add the groundwater surfaces, which again represent both the high and the low water table levels. And these surfaces Steve created in Surfer by using the gritter. And so these will give us a good picture of where the LNAPL concentration values are located compared to the water table once the data has been added. So I'm going to go now and import both of these grid files using the same workflow that I used to import the ground surface. So please just give me a second here. Now, high groundwater grid. And again, we want this to locate correctly, so this option of import as a curvilinear lattice needs to be used. And again, we can render this with a 3D surface or a height field. I'm going to change the color map just a little bit. And I'm going to reduce that opacity to about 40% or so. Again, the other surface, which was the low groundwater surface, again, is a curvilinear lattice. And let's add a 3D surface here. I'll go ahead and change this opacity. And so, right? And you can see now that both the surface, the high and low water table surfaces have been added, but there's really not a lot of separation here. You can see that I'm circling that with my mouse on screen. So we can account for this really easily, quick and easily, by adding some vertical exaggeration. So I've clicked the viewer window module up in the network manager, and I'm going to go down to the property manager and give it 3 times vertical exaggeration. Let's fit that back to the window. And yeah, you can see that there's some stretching going on here, but we still get a good idea of what's going on. And more importantly, we can see a little bit of space here between the high and low groundwater grids or surfaces. So at this point, I'm going to go ahead and import the sparge wells. And again, I have already taken the liberty to export these as 3D DXFs from Steve's model. And since this model doesn't use the data that's rendered along these wells, I think this was appropriate. So I'm going to go ahead and do this real quick. Okay, and these were the monitoring wells that we saw in Steve's project, right? And just for completeness, I went ahead and imported those. And so now we really get a good sense of what the project looks like and what Steve was used to create for his project and for the stakeholders within his project. And so we see the services and the DXF files. Let's really get to importing the meat of the project, which is the borehole data. And before I'm going to do so, I'm going to turn these monitoring wells off just so we reduce a little bit of the clutter. And I'm going to go ahead and import the borehole data. So again, I'm going to start this process off by file import. And since Steve used the multiple table approach when organizing the borehole data, I'm going to first select the UVF collars table, okay, and import the collars table first. Go ahead and click open. And now you can see that the collars table has been imported. And I need to go down to the property manager and set the appropriate columns. So first, if I expand this up just a little bit. Okay, and so first, we have our output type. And since this is borehole or well data, I need to change this to wells. Next, under well columns, and you can probably notice that all my columns have changed here. And these will change again as soon as I change this to collars. And then for well name, I'm going to go ahead and select column A. And then I'm going to assign the rest of the appropriate columns. So for the easting, that'd be top X or column B. For the northing, that'd be top Y or column C. And for the elevation, we're going to use top Z. This data does include azimuth variables as well as dip. So I'm going to set those appropriate columns. And then finally, I'm going to set the total depth. Okay. So now that we have all the data columns properly set in the property manager, I'm going to add a well data module and then a well render module. So I'll show you an example of this so we can see where these boring locations exist within the model. So to add the well data module, which is a container module, and this is necessary when we're using the multiple table approach, I can right click on top of the callers table inside the network manager, and from the context menu, select well and then well data. You see our well data module, and again I can right click here, go to graphics output and well render, and then we can see the boring locations here within inside of Steve's project. Now, of course, these boring diameters look a little bit too big, so let's go ahead and change that. So I have the well renderer selected. I'm going to go to the path data tab, and I'm simply going to type in a new size here. 0.5 would be appropriate, I think, right? And so we can see these locations here, right? And rotate this down, and you can see that the boring locations do go below both the high and low water table. So as Steve indicated earlier, he did collect UVF samples along these borings, which again was used to find the concentration levels of the LNAPL, and also used to delineate certain concentration level extents. So the next thing I need to do here is to load the sample data into the project and then render it along these borings I just imported. Okay, so I'm going to go back up to the File menu and click File Import. And the import dialog, I need to use the From To data. I'm going to select that in my import dialog and click Open. And you can see that this has now been added to our network manager. And again, we needed to assign the appropriate columns in the property manager. So I'm going to go ahead and do that right now. Again, the first thing that I always want to make sure that the output type is set to wells and not points, because this is borehole data or well data. And I'm going to change my sheet type here to From To logs, because we know we're working with From To data. And I'm also going to change my log column down to 1. And I'm actually going to pull the log value here to render along the borings. And now that we have all this data, these columns set, we can render the data along the well renderer easily by dragging this connector up to the well data module, using worksheet B as our connector. And then let's take a look at what this data looks, this interval data looks like when we render it along the boring tubes themselves. So with the well render selected, I'm going to go to the interval data tab. First thing I'm going to do is check to show intervals. My data source is From To values and not log values. So I'm going to leave that set. And then I'm going to pull up my column G as my log. And you can see that we've got a diameter issue again, and I'll address that here in just a second. I'm going to change my color method, though, to by log, and change my color log also to column G. For the color mapping, let's go to rainbow. And the size method, I'm also going to change that to by log and use column G. And then finally, let's reduce that diameter a little bit here by changing the size to 1. Okay, and so let me zoom in here just a little bit and kind of move up. And now you can see this data, concentration data, UVF data, that's been rendered along the boring locations here. So now that the borings and the water table levels have been added to the model and the 3D DXFs have been added, it's time to grid the data from the borings. So I've already extracted the data from these borings into an Excel file, which is going to be used as input to the gridder. So let me go ahead and load the point data into the project. Okay. Again, I clicked File Import. I'm going to select my extracted data, Excel file, and click Open. And now I need to go find this data and do the same thing I did with the borehole data, and set the appropriate columns or assign the appropriate columns in the property manager. Okay, and so with the point data selected, I'm going to change my output type now to points, and assign my eastings for the x coordinates, the northings for the y coordinates. We're going to use a midpoint elevation, which Steve derived himself. And that would put the data point right at the middle of all these intervals, these 2-foot intervals. Okay, and then I have one component that we're going to grid here, which is going to be the TPH value inside of the data. All right, and now that we have the columns set appropriately for the point data, I can right-click and go to Computational and add a gridder module. Right, and so we can see the gridders right here. And then let's go ahead and drill down into the gridder module and change some of the properties here before we grid the data. So with that gridder module selected, on the General tab here, we can see a few parameters. Steve used inverse distance as his gridding method. And then he changed the and isotropy to and isotropic, where he changed the x length to 55, the y length to 55, and of course this is refers to units. Voxler doesn't know units, but I know the data is all in feet, so this is going to extend the ellipse of influence to 55 feet in both the x and y directions, and then also 3 feet in the z direction. So we're going to have more influence when gridding going in the x and y directions, simply put, than we are in the z. Now Steve also used a similar search type. Okay, so I'm going to put in about the same settings here, and what changing the search ellipse will do is it'll only take data points when finding the lattice nodes or assigning the lattice nodes that are within this search ellipse. Okay, and so both of these two settings work together. And so now that we have all the parameters set for the gridder, I can go down next to Action and click the Begin Gridding button. So Voxler's gridding the data. That was fast. Only took just a few seconds to grid the data. And so now we can, now that the data is gridded, we can delineate the concentration in the soil of the jet fuel or the LNAPL by adding an isosurface to the gridder. Okay, and so we can simply right-click on top of the gridder and use graphics output isosurface, right? And you can see it down there a little bit. I'm going to go ahead and change this color mapping, right, to rainbow. And again, I know I mentioned this earlier. The target ISO values here for this data is going to be anywhere from 2,000 to upwards about 6,000, right? And you can see as I increase the ISO value here, we're going to see the concentration levels. I went a little too far there. Let me just set that to 6,000. That the concentration levels do decrease. Okay, and so now we get a really good view of the complete conceptual site model that Steve used, right, for this project. And to deliver this project to the project stakeholders, Steve exported using file export from Voxler and exported to an IV format the entire project. That IV, resulting IV file, was used in a product called, this is a third-party product, called PDF3D, which creates 3D PDFs. Okay, and so that 3D PDF can be easily viewed by everyone involved in the project, sent to all the stakeholders, and easily emailed. And so the product PDF3D, it's not something that we do endorse, but we like an awful lot, and it has been optimized for use in Voxler. So let me go ahead and pull that up really quick. Okay. And so this is what you see on screen now is a good view of the 3D PDF that Steve used to submit to his clients. You can pan around here and you can see there's full 3D rotation. Okay, and so you can see all the elements that we saw in Voxler. We do have some labels there. Transmission lines, the isosurface, both the high and low water tables, the vault, and of course the treatment building. And so before I open it up for any questions, I'm going to go ahead and turn it over to Steve for just a few minutes so he can give us a few words about the model. So Steve, I'm going to go ahead and unmute you. There you go.
All right, thank you, Drew. Nice job. So I just wanted to kind of conclude here to give my interpretations of the model and give the audience some things to think about. This site was not a particularly large release at 9,000 gallons. At least to me, I've dealt with releases up to 5 to 10 million gallons. So from the standpoint of the LNAPL release, this was not a particularly complicated site. Drew and I liked this site from the standpoint of the addition of the DXF elements and the piping and so forth. So we think it's a nice model to use for this purpose. What you don't see in this model is you don't see a lot of contamination beneath the vault down to the water table. There is some, you can see color along the borehole paths, but generally because this is light JP8 fuel, probably the soil vapor extraction and sparging has stripped out a lot of that contamination. I would say that the client in this particular case was both a client as well as the regulatory agencies. My client was a consultant. Their client was the Air Force Civil Engineering Center and Defense Logistics Agency. They were very pleased with both the performance of the Voxler model, and then with the addition of the 3D PDF file, that really gave some interactivity between myself and my client and their client, the regulatory agency. So the 3D PDF really is a great method to take Voxler and share it with your project stakeholders. So I think that's probably wraps up my thoughts on that.
Thank you, Steve. So at this point, I'm going to go ahead and open it up for any questions that remain unanswered. So if there's any questions, I'm going to ask my host to go ahead and send those on over to us. And you're more than welcome to stick around and ask us anything you'd like. And if not, I'll be concluding the presentation shortly. Okay, it looks like we've gotten most of the questions answered. So this is going to conclude the presentation today of the groundwater remediation case study. And so hopefully everyone found the information I covered today useful. And so if there's any additional questions on what was covered today or anything else, just please contact our tech support team. And then, Steve, did you have any concluding words that you wanted to give us?
Yes, thanks, Drew. So I just wanted to invite anybody in the audience, if you have questions more on the LNAPL characterization side of this as opposed to the Voxler side of it, feel free to reach out to me. You can email me directly at the email address shown at the bottom of the screen. Some of the imagery from this project and others you can see on my Facebook page. I'm always happy if people try to connect with me on LinkedIn. And then finally, just there is available online a video of a presentation that I did for my professional society, which is called the LSP Association, which is uses this site as a case study, not so much focused on the imagery, but more of the site assessment. And you could go to facebook.com/lsp.association, and there is a video there from January getting very deep into the LNAPL technical aspects of this site. So I appreciate anybody that wants to reach out, and certainly thank everybody for attending today.
Thank you very much, Steve, and I appreciate your time today as well. And so for everyone, we are concluding. There will be a recording posted on our website shortly. And I wanted to say, as always, we really appreciate your time. Thank you, everybody.